welcome to the deep dive. Today, we are jumping straight into the future. And maybe surprisingly, we're doing it with an element you probably think of as, well, ancient gold.
That's right. We've been looking at some really surprising research coming out of Penn State and Colorado State.
And it suggests that gold, specifically, nanoscale gold, might just hold the chemical key to solving one of the biggest roadblocks in advanced computing.
It's a huge one. I mean, the promise of quantum computing is this world-changing power. But the reality is that actually scaling those systems up, that is still a monumental hurdle.
So our mission today is to unpack that. First, the physics of that hurdle, this trade-off between accuracy and scale.
And then we'll get into how these gold superatoms are somehow managing to replicate the absolute best, most pristine quantum systems, but in a totally scalable and customizable format. Okay,
let's start at the beginning. The fundamental principle. Everything we're going to talk about, quantum system sensors, all of it, it really boils down to the behavior of electrons.
Specifically, their spin.
Exactly. We can't really move forward until we nail down what spin polarization actually means.
Absolutely. The electron spin it's the foundation. It's an intrinsic property.
Right.
And maybe the easiest way to picture it, for us lay people anyway, is to use that classic analogy.
The Earth, right.
Yeah, the Earth.
So we can picture an electron spinning on its axis. It can go either clockwise or counterclockwise. And just like the Earth, its axis is a little bit tilted.
Precisely. And in quantum information, that spin direction, up or down, clockwise or counterclockwise, that's your qubit. That's your 0 or your 1. But, just having one isn't enough. The real magic happens when you get a huge number of them in a material to all agree.
And that agreement, that spin polarization.
That's it. When many, many electrons align their spins in the same direction and their tilts all match up, they become highly correlated. And that high correlation is high spin polarization.
Okay, so why is that so crucial? Why do you need that for a functional quantum computer?
It gives you two things, really, accuracy and longevity. Longevity is often called coherence time.
Coherence time?
Yeah. When the spins are all perfectly lined up, they're much less susceptible to outside noise. And that means the material can hold on to the information, the quantum state, for a much longer time. And in the quantum world, we're talking microseconds. But every single one of those microseconds matters.
And that perfectly sets the stage for the core problem we're trying to solve. We know how to get phenomenal coherence, but that solution just isn't scalable. We're in the scalability trap.
We are. The current, let's call it the technical gold standard, for these really low-error quantum systems, it relies on using trapped atomic ions.
Which sounds incredibly fragile.
Oh, it is. These are atoms that have an electric charge, and they're suspended or trapped in a very, very controlled gaseous environment.
And expensive to maintain, I'm guessing?
Very. But the performance is just unmatched. Because they're so dilute and isolated, their electrons can be excited into what are called Rydberg states, and we really need to pause on that term.
Okay, let's do it. What makes a Rydberg state so special and so delicate?
A Rydberg state means the electron has been pushed into a really high energy level, so it's orbiting extremely far away from the nucleus.
So like a satellite in a very high orbit.
A perfect analogy. Think of it like a high-altitude weather balloon. Because it's so far out, it interacts very strongly with other distant Rydberg electrons. And that's fantastic for computing. It allows for this huge synchronized spin correlation.
So this is how they get that holy grail of superposition, the ability for an electron to be a 0 and a 1 at the same time until you look at it.
Correct. The Rydberg state's unique properties are what allow for that long-lasting superposition and that precise spin polarization. But here's the catch.
There's always a catch.
It's a high-altitude weather balloon. It's incredibly easy for any tiny interference, a little temperature fluctuation, a stray electric field to pop it.
And because they're these dilute gaseous ions, you can't just pack them together to make a computer chip. They're stuck in a lab.
Exactly. Which brings us right to the condensed phase dilemma. If you want a chip, you have to move from a gas to a solid. A condensed phase. You have to pack those atoms together.
And the second you pack them together, you get the scale, but you lose that pristine, isolated environment.
And boom, suddenly the whole system is exposed to all the noise that exists in a solid. Thermal energy, vibrational noise, everything. All that noise just rushes in and scrambles the delicate quantum information.
The coherence time just drops.
To near zero. The error rate goes through the roof. And that's it. That's why building a large, functional, solid-state quantum computer has been so incredibly difficult. It's the trade-off.
Scale versus coherence.
You got it.
Okay, so this is where it gets really, really interesting, because this research we're diving into today suggests that these gold nanoclusters might just resolve this exact conflict. They act like those pristine gaseous ions, but they're in a solid.
Right. The breakthrough is really in the synthesis of these unique gold structures. The researchers have created what they call gold nanoclusters.
And they use the term superatom for these. Why that name?
It's because of their electronic character. These clusters are incredibly small, tens or hundreds of gold atoms. But at that tiny scale, their combined electronic structure, and now we know their spin properties, they behave just like a single, highly controllable, ultra-precise atom.
I have to stop you there with a really practical question. I'm sure you, the listener, are thinking it too. Why gold? It's famously expensive. If the goal is large-scale production, why not copper or something cheaper?
That's a great question. And it's not about PR, it's pure physics. Gold atoms at the nanoscale are just unique. They are unbelievably stable and chemically inert. And most importantly, they hold on to their electronic structure even when you bond other molecules to them. That structure is what allows for these critical quantum states. Other metals, they just oxidize or destabilize.
So that stability of the gold core is everything. Let's talk about the structure. How are they built? How are they protected?
They're what we call monolayer protected clusters. So you have the gold core, and that core is completely wrapped up in a layer of specific organic molecules. We call them ligands.
So it's like a tiny chemical jacket.
A perfectly fitted chemical jacket or a shield, yeah. And the beauty here is that it's not a fixed thing. You can precisely adjust and customize these clusters just by changing the molecules in that ligand shell. And unlike trapping ions, you can make these things using fairly standard chemistry in pretty large quantities.
But the real proof is in the pudding. Can they actually replicate that high-energy, delicate Rydberg behavior? Did they find superposition?
They did, and this is the core scientific achievement, really. The team identified an astonishing 19 distinguishable and unique Rydberg-like spin-polarized states inside these solid gold clusters.
19 in a solid material. That's a huge library of states to work with.
It's proof. It's proof that they have successfully transplanted the key quantum properties of the best gas phase systems, that ability to be in multiple long-lasting superposition states, into a chip-friendly condensed material. It's a huge leap.
Okay, so that alone is massive, solving the scalability versus accuracy problem. But the next part of the discovery, I think, is where it gets even more wild, this idea of active customization.
Yes.
Traditionally, a quantum material has its properties, and they're fixed. Silicon does what silicon does.
That's the rule. A material has X amount of polarization. If you need something different, you have to go find a whole new material. But these gold superatoms, they completely smashed that rule. The research showed their quantum properties are actively tunable.
How? How does that work? Is the gold itself changing?
This is what's so fascinating. The quantum ability isn't controlled by the gold. It's controlled by the jacket we put on it. The spin properties of the electrons in that gold core are intimately related to the physical microscopic vibrations of the ligands surrounding it.
Wait, hold on. So the actual physical movement of the protective jacket is controlling the quantum state of the core.
Yes.
That sounds like controlling physics with chemistry.
That's a perfect way to put it. It's a profound coupling. These organic ligand molecules are vibrating in very specific ways, and that mechanical movement couples directly to the quantum state of the electron, spins in the gold. It's like you're controlling the quantum property by playing a tiny chemical drum. You change the drum skin, you change the beat, and you change the quantum outcome.
That is genuinely revolutionary. Did the data back this up? I mean, what kind of tuning are we talking about?
Oh, it did. Big time. They tested clusters with 2 different ligand shells. One cluster showed a 7% spin polarization, which is, it's a decent value.
Okay.
But then just by swapping out that ligand coat for a different molecular structure, they got a polarization level of nearly 40%.
40%. Just from changing the jacket?
Just from changing the jacket.
Wow. How does 40% stack up against other leading materials? Is that competitive?
40% puts these chemically synthesized gold clusters right on par with some of the most complex, difficult-to-make 2-dimensional quantum materials that are being researched right now. It proves this isn't just a curiosity, it's a high-performance system.
So the implication for design is just monumental. Instead of searching for a material that happens to have the right fixed value, researchers can now say, okay, I need this specific property, and then go engineer the ligand structure to deliver it.
This is the massive paradigm shift here. I mean, historically, quantum information science has been dominated by physics and materials engineering. Finding the one exotic material and then isolating it perfectly.
And now,
And now this opens a whole new frontier for chemists. They aren't just making a container anymore, they're designing the quantum function itself. They can use the huge toolkit of organic chemistry, that precise control over bonds and structure, to tailor the quantum results at an unprecedented level. They're literally building the rulebook for how molecular chemistry translates directly into quantum behavior.
so it decentralizes the problem. If the quantum property isn't good enough, you don't need a new exotic core. You just need a better ligand.
It democratizes the whole design process. It could speed up development so much, and it offers a real pathway to mass-producing customized quantum components. We're moving from just discovering materials to truly engineering them.
Let's sum this up then. What's the so what for you, the listener?
The takeaway is clear. These gold superatoms offer a scalable, tunable foundation for the next generation of quantum devices. They've reconciled the two biggest conflicting needs in the field: the need for high accuracy and the need for a practical, scalable material.
And the research team, they're not done, right? What's their next step?
They're focusing on deepening that chemical rulebook we talked about. They want to figure out exactly how changing specific little features within the ligands affects the spin polarization. This fine-tuning will let them move from a proof of concept to having basically a precise dial they can turn to control quantum coherence.
It's just amazing that an element as old and familiar as gold, when you look at it at the nanoscale and protect it with just the right chemistry, might hold the key to the next quantum revolution. This feels like a breakthrough that could really accelerate things.
It does, and it raises a really interesting question, one for you to think about as we wrap up. If chemists can get this level of precise control over a fundamental, previously fixed quantum property like just deciding the spin polarization by designing a molecular coat, what other stubborn material constraints might be solved the same way? Simply by engineering the right nanoscale chemical structure.
What other rules are just waiting to be rewritten by a better jacket?
Exactly. The potential for molecular engineering to rewrite the rules of material science. I think we're only just beginning to see it unfold.
A fascinating thought to leave you with. Thank you for joining us for the deep dive.
Until next time.